There we go. All right, so a logarithm. Log base A of B is equal to C. The log is equal to the exponent. So whatever this base is the base of your exponential. Whatever it's equal to is the exponent, and then whatever you're taking the log of is what that exponential is equal to. So our first job is our first two jobs is we're gonna take logarithmic statements and rewrite them as exponentials, and then we're gonna go the other direction. We're gonna take exponentials and rewrite them as logarithms, and just get used to that property. That's useful when we start solving some equations today. If you can rewrite them that way, then the solving of the equations can be easier one way or the other. Okay, you'll see it as we go along. It really isn't that bad. It seems like a really complicated topic because of the name, but it's not. So we're going to rewrite the log function as an exponential. Okay, y equals log base 3 of x. Okay, so we're going to rewrite this as a exponential because it's logarithmic. So if we're going to rewrite that as an exponential, what's the base of our exponential? 3, because that's the base of our log. Okay, what is the log equal to? Y, which is the what? The exponent, always. So we have 3 to the y is equal to x. And you're done. Not much more to it than that. We had log base 2 of x equals 3. And this is where we kind of melt into solving an equation with this, because here we have the x in there and we got numbers everywhere else. So if we can rewrite this as an exponential, maybe we can figure out what x is. So what's the base of our exponential? 2 with an exponent of 3 is equal to, there's an equation that I think we could solve, right? Because we know what 2 to the third power is. Are they always going to be that easy? No, absolutely not. But that's the beginnings of it. To get that idea, if you can get there, things go better. So we had log base 5 of 1/25 is equal to x. Again, we're just rewriting it. We're not solving anything yet. We're just rewriting that. So what's the base of our exponential? 5 with an exponent of x is equal to 1/25, because that's the only thing left. And then being able to rewrite that logarithm as an exponential like that, this would allow us to do some tricks with exponents that we know stuff about to solve a logarithmic equation. Okay, so there's a lot of benefits to being able to rewrite here. Natural log of x equals y. And this is where, we get the definition of natural log. If you don't remember it from Algebra 2. A natural log is kind of like it's kind of like pi. It happened enough in a lot of experiments that they decided to give it its own kind of thing. Natural log is really log base e. But they said, natural log happens enough. We're gonna give it its own name. We're gonna call it natural log. Ln is log base e. Okay, so that's when you see Ln, this is what you want to think, log base e. They're not going to write it this way. Hardly ever will you see that happening. But they'll write natural log. But it's this. So if we're going to rewrite that as an exponential, the base is now what? E to the what power? Y equals x. E is a number. E to the first power is about 2.71 and some change, a whole bunch of decimals after that. It's a number. Okay, E is kind of like, it's not exactly like pi in where it comes from, but it is a number that's it's a common number. A lot of you do things in biology, experiments in there, you use natural log and E a lot in biological experiments and bacterial growth and that sort of stuff is where that's happening at, or it tends to happen a lot at. Let's do one more of those. Log of x equals 3. All right, so this is another common log is what it's called. Natural log is a common log. Regular log is a common log. Absolutely. Why is it the base of 10? Couldn't tell me why. Okay. That's to me, that's the interesting question. That is a base of 10 because what kind of number system do we live in? We live in a base 10 number system because you got a ones position, that's 10 to the 0 power. We have a tens position, that's 10 to the first power. We have a hundreds position, that's 10 to the second power. We have a thousands position, that's 10 to the third power. The number system we live in is a base 10 number system. So a common log that they're not going to write that 10 there. There's not a 10 there or anything else, then it's base 10. Okay. A common log is base 10. So as an exponential, this would be 10 to the third equals x. And there we could get what x is. It's 1,000 easily. Okay. So that's going from a logarithmic statement into an exponential. Let's go the other direction. Rewrite it as a log. 3 to the x equals 27. What's the base in that exponential? 3. So to write it as a logarithmic, it's going to be log base 3. What's the logarithm always equal to? The exponent. What's the exponent in this case? X. So it leaves one spot for the 27. Right there. Ten to the x plus 1 is equal to y. What kind of log base do we use? Log base 10, which is just plain log, right? Of y is equal to x plus 1. Remember, your log is always going to be equal to the exponent. Okay? That's the key to rewriting. A to the fourth equals 24. What kind of log base we got here? Log base A of equals, yeah. Log base 5 of 25 is equal to x. Remember, it's always equal to your exponent. E to the square root of x is equal to y. The base is E. Be natural log. Very good. Absolutely. The base E is natural log ln of equals square root of x. Remember that whole exponent there. So rewriting from logarithmic to exponential, and then from exponential back to logarithmic. Being able to do that going to be helpful. I know that. All right. Now let's actually apply that to solving some equations and see, or evaluating some logarithms without a calculator. So let's take log base 2 of 16 equals x. All right. So this is kind of like solving an equation. If we're going to, like, I'm setting it up as an equation right now. They may give you the problem, just say that, and say evaluate it. When they do that, what I like to do is say, okay, if I'm going to evaluate that, I'm going to say it's equal to x. And then I can rewrite it as an exponential, because I'm just introducing a variable to that. Okay, that makes rewriting as an exponential really easy. How do we rewrite that as an exponential? And we can think in that terms pretty easily. 2 to what power gives me 16? 2 to the 4th power. So x must be 4. So log base 2 of 16 is equal to 4. You get that as the evaluated result here. What if they told us like log base 4 of 1 over 64? They said evaluate that. They said do it without a calculator. So I'm going to equal it to some variable. You can pick x, or you can pick whatever letter you want to. Just don't pick e. Don't pick x. All right, so it'd be 4 to the x power equals 1 over 64. Think about what 64 is in terms of a 4. 64 is 4 to what power? Yeah, 1 over 64 to be 4 to the negative 3. If 4 to the x is equal to 4 to the negative 3, then what does x have to be? Negative 3, right? If those are going to be equal, then the exponents have to be the same, right? So x would have to be negative 3. That's really, that's really the idea of solving some of these equations. We're going to get more complex than this, but evaluating a log and solving an equation of a log can be done easily using exponential notation instead of logarithmic. That it makes it a lot easier to do, in my opinion. All right. Log base 3 of 81. Evaluate that. That would be 3 to the how many? 4th? We go through the motions of doing all that stuff. It's 3 to the x equals 81. And we know that 81 is 3 to the 4th power. If you don't know that, you can do a factor tree for 81 and start breaking it down. 9 and 9, and then 2 9s become 4 3s. And that's how you get 3 to the 4th power. So x would equal 4. That's 4. That's what that evaluates as. I'll show you how to check that with the calculator, because it's handy to do that, right? With the graphing calculator, you've got a log base function on there. That log base function is under the math key. So we're going to hit the math key. Everybody get yours out. Okay, catch up here. Unless you're using an 83, yours should do this. If you're using an 83, then I'll show you another way in just a second. And sometimes I even use the other way, even though mine will do this. Sometimes it's easier. Okay, so you hit the math button, and then press the up arrow. And you notice there, selection A, or there's a selection somewhere on your list that says log base. Select that one. Does it come up looking like that? Because anybody's not doing that. If it's not, there's probably just a setting we need to change. Okay? got a blank right there for what base are you doing, and then it's got a blank here for what you're taking the log of. So if we did log base 3 of 81, we could put a 3 right there, press the right arrow key to get up into that spot in 81, and hit enter, and we get 4. It evaluates that for us. Okay, that's using the log base function of your calculator. There's a thing called the change of base formula that you can use if for some reason you're on a test that doesn't allow a graphing calculator, or for whatever reason you don't have a graphing calculator with you, or you only have access to a scientific for some reason. You can use the change of base formula that if you're doing a log base x of y, the change of base formula says if I just do the log base 10 of y over the log base 10 of x, or natural log of y over natural log of x, either of those will give me the same result as this. So if on my calculator it doesn't have a log base function, well, notice down here on the delay's killing me. Down here on the left side of your calculator, you've got a log button, the log base 10 button, and yeah, no. All right, back at it. So on a calculator, I've got a log and a natural log button. Those are the common logs, and they're common, so they put a button there for them instead of having to go through a menu to get to them. The log button, if I do log of 81, close the parentheses, divided by log of 3, I should get 4 back as the answer. And I do. Same thing happens as if I use natural log of 81 divided by natural log of 3. You get that same result. So that change of base, sometimes it's quicker just to type it in that way instead of hitting math and having to find long base and all that stuff. So sometimes I just use that anyway, just because I can punch those buttons a little quicker sometimes. But if I'm ever in doubt about how putting it in there, I always do that log base. Okay, so change the base formula. I've shown you that. We used to not have graphic calculators, did all this fancy stuff. So you needed that to be able to do that. We used to have in the back of the book a table of evaluated logarithms, and you had to, if you had to find the log base 3 of 80 of some number, maybe it's not 81, it's a one that doesn't work out nicely. You had to go back to the back of the book and look up, okay, what's log base 10 of the big number? What's log base 10 of the base? And then you had to divide those two answers. So you had to look things up in the table. That's back in the old days, you know, back when we rode horse and wagon to school and stuff when I was a kid. So, but I've shown you change of base. It exists. Do you use it very much in today's technology-driven world? No, probably not. But it's there and it's handy sometimes. Okay. All right. Let's talk about functions. The name of the section was logarithmic functions. So let's talk about the function stuff. Functions talk with logarithms. A logarithm as a function changes y to f of x. We have log of some base of something of x. There you go. All right, so guys, back up for the time being anyway. All right. I said we were. There we go. All right. Log functions. Okay. When we're taking the log of a number, we can only take the log of positive values. Okay. So that means whatever we're taking the log of has to be greater than 0. Greater than 0. So if it's log base, doesn't matter what base it is, whatever we're taking the log of, we're going to set that greater than 0 to help us find the domain. since this is just x in there, our domain is from 0 to infinity, not including 0. We think about in terms of exponents, if we raise a number to an exponent, is there any exponent that will turn 10 into 0? Because 10 to the 0 power is what? 1. And then 10 to a negative 1 power is 1/10, right? Negative 2 power would be 1/100. So we never get to 0 there. So we can only take logs of numbers that are positive, so from 0 and above. So whatever we're taking the log of to find the domain, we're going to set that greater than 0 to find that domain. The range, this is the easy part, is going to be from negative infinity to positive infinity. Doesn't change. Okay. Okay, so we'll put a star here. We never take log of 0 or negatives. That's an important thing, because that's going to come up when we do equations, when we solve equations too. The logs of negatives or 0. Right? We can't have that. All right, so we're going to state the domain and range. We'll glance at the graphs of these two. Okay, so example N. Thank you. F of x log base 2 of x plus 3. Okay. All right, so we have something a little different inside of that log there. It's not just plain x, it's x plus 3. So if we're going to find the domain of that, we're going to take whatever we're taking the log of, no matter what the base is. The base really has no bearing on the domain of this thing as far as how we find it. Okay, it changes the shape of the graph a little bit, but it didn't change how we find the domain. We're going to take x plus 3 and we'll set it greater than 0 and just solve it. Subtract 3. X is greater than negative 3. So our domain in set notation be all x's such that x is greater than negative 3. In interval notation, be from negative 3 to infinity. The range is going to be from negative infinity to positive infinity. Nothing's changing on that. Okay. Let's look at the graph of that just to get an idea of what these graphs look like. Okay. I've got something kind of in here a little bit. X plus 3, change that, and I'm going to delete the other stuff. So I'll just go through the whole motion. So math, press the up arrow to get log base. We get log base 2 of x plus 3. Hit graph. We can see the resolution kind of eats us up here because it gets almost completely vertical here, but not perfectly vertical. There's really a vertical asymptote on this at negative 3. At that value that we can't go below, there's a vertical asymptote there. And so this line is just getting steadily closer and closer to that vertical asymptote. Remember, we did vertical asymptotes with rationals. That's what happened there. And then this, it gets pretty flat here, but it still is inching upward the whole way. So the range from negative infinity, this line keeps going down. This is ever going to get slowly and slowly, really, really slowly get toward positive infinity. Eventually, the x would be really, really large to get there. But we get the shape of the graph. It's similar to like a square root type function, but a little bit different. The curve is a little steeper here on that front end for that. So that's a log base 2 graph. And we can see that domain happening there from negative 3 up to positive infinity as we go across there. Okay. Let's look at one that's a little more interesting. F of x equals log base 5 of 1 plus x for 1 minus x. So a rational expression inside of the log. So we've got to find the domain of that. So this is a little bit more difficult because a rational expression is a fraction, and we need to know when that fraction is going to be positive. So with fractions being a positive fraction, you have to have either positive on top and positive on bottom, or negative on top or negative on bottom. Both of them have to be the same. So when we look at that, if we set this inequality up, we can't just cross multiply here and work things out. It doesn't work for us there. We've got to think about the pieces that would cause this thing to equal 0. And that's where we're going to have. So we look at the numerator, 1 plus x. When is it equal to 0? When x is negative 1. 1 minus x. When is it equal to 0? X is positive 1. So we take the numerator, set it equal to 0, and solve it. Take the denominator, set it equal to 0, and solve it. Then we set up an interval test. With those values on a number line. Then we've got to check. We've got 3 areas to check. We've got numbers that are less than negative 1. We've got numbers that are between negative 1 and 1. We've got numbers that are greater than 1. We've got to check each of those areas to see what kind of numbers this inequality gets. Okay? So let's pick a test value that's less than negative 1. Negative 2 would be a great one. You could pick negative 1.5 if you wanted to. I don't know why you would, but you could. Just any number that's less than negative 1. So negative 2 is a great one to try. So if I plug that into this inequality, 1 plus negative 2 would be what? Negative 1, right? 1 minus negative 2. Positive 3. So we have negative 1 over positive 3, which is what kind of fraction? Is that greater than 0? No. So that area is false. So we know that's not going to be part of our domain. Okay. Let's pick a number that's between negative 1 and positive 1. 0 is the best one to pick. We're going to test that. 1 plus 0 over 1 minus 0. It's 1 over 1, right? Is that greater than 0? Yes. So this area is true. It's possible that that's the only true area. But it's also possible that this area could be true as well. And so we got to plug a number in that's greater than 1 and try it. 2 is greater than 1. Let's use it. 1 plus 2 is 3. 1 minus 2, negative 1. So 3 over negative 1, is it greater than 0? No, it's false. So our domain is only the numbers that are between negative 1 and positive 1. Okay? Yes, sir. Because there's something different in here. It's whatever you're taking the log of, you're setting that greater than 0 to work with it. So when there's something different in here, yeah, your domain is going to be different. Always. There. So the inequality from between negative 1 and positive 1 would be negative 1 is less than x is less than 1. Negative 1 to positive 1. That's the interval notation. The range. Let's glance at the graph of this just to get a good idea of what's going on there. So I'm going to do math, log base 5, parentheses 1 plus x, close parentheses, divided by parentheses 1 minus x, close parentheses, graph. What's the range? Yeah, it doesn't look like it, but what does this line keep doing? Keeps going straight down. This line keeps going straight up. There's these vertical asymptotes here Remember, it's still going as we get toward -1. So the range is still from negative infinity to positive infinity. That hadn't changed. Even though the graph doesn't really look like it when we draw it on the graphic calculator. That is what's happening. Okay. What if we throw an absolute value of x in there, which is close to what we started with, Tristan? Like you said, it was just an x in there. We had from 0 to infinity. We throw an absolute value in there. It's really close to that, but it's a little bit different because it's an absolute value. What do we know about absolute value of x? When is it greater than 0? Always? Oh, when it's not 0 though. It's every number except for 0. So this x does not equal 0 is going to be our domain for that. What's the interval notation for that? There you go. Good job. What's the range? Guess what? It's the same. Yeah, doesn't change. Simplifies life for that range. Doesn't change. Pretty nice. Okay. I dread when my oldest gets to that because he's just now learned to write an 8 really well. So it's fun. All right, so it's log base 13. It doesn't really matter. Of the absolute value of x plus 2. So let's complicate that absolute value idea and make it a little bit bigger or a little more stuff in there. So we got absolute value of x plus 2 in that. So again, we're looking for the domain and the range of this. So to find that domain, we need to know when is the absolute value of x plus 2 greater than 0. So x can't be -2, right? Because any other number we put in there, it's going to give absolute value is always going to be positive, right? Because it's a distance from 0, a distance always positive. So anything except for -2. -2 would give us a value of what? 0, which is the one that messes it up. So x does not equal 2. So our domain would just wrap it around, or -2, excuse me. That's what y'all said. Go from negative infinity to -2, union -2 to positive infinity. That's our domain. Range, negative infinity, positive infinity. Right. So, domain, set whatever you're taking the log of greater than 0 and solve it. That's going to get you your domain. Range, not going to change. All right, let's get to the last thing in this section, and that's solving equations, which is, I like that better because you get x equals a number and you feel like you've done something and you can check it and all that stuff. So solve. So we're going to use some of the skills that we've talked about today to solve some logarithmic and exponential equations. Log base 3 of 4x minus 7 is equal to 2. Okay. So this is a logarithmic equation because it has log in it, right? But it doesn't have log on both sides. It just has it on one side. And anytime you see that, you want to think, hey, could I rewrite that as an exponential and just get some numbers out of it? How would I rewrite this as an exponential? 3 to the second power is equal to 4x minus 7. What's 3 squared? It's 9. We know that number. And then hey, that's an equation that I can do, right? Okay, so we'll just get x by itself now. Plug that in. You know, get 7, move it over there. 9 plus 7 is 16. 4x, 1 by 4, and x equals 4. Now, we need to check that in the original problem because we need to make sure that 4 doesn't get us a negative inside of the log. So if I plug that in, 4 times 4 is 16. 16 minus 7 is 9. That's a positive number, so that's okay. And log base 3 of 9 is 2 out of that. Okay. Did you have a question, Kyle? No. Oh, you just stretched. Okay. All right, good deal. All right, let's look at another. Log base x of 64 is equal to 2. So we got an x in the base here. But it's a log on one side and not on the other. So how could we rewrite that as an exponential? Yeah. Okay, and then we take the square root of both sides. Plus or minus 8. Because we introduce the square root. Anytime we introduce a square root to a problem, you got to put plus or minus. Now, that base can be negative. This in here cannot be. That's the difference. The reason we got to keep both of them there. Because negative 8 squared is still 64, right? So it still satisfies that equation out of that. So plus or minus 8 on that one. Log base 3 of 3 to the 6x equals 42. Do I? Can I do this just like I did the last two? Yeah. It's got a log on one side and a number on the other that's not a log. So I could just rewrite it as an exponential, couldn't I? Yeah. 3 to the 42 was 3 to the 6x. And if you know that these are the same base, then what do the exponents have to be? They have to be equal to each other, right? So 42 has got to equal 6x. Divide by 6. 42 is got to equal 6x. So 42 divided by 6, 7. There's also a log property, which we'll talk about on Thursday, that those two just cancel each other and you go straight to the equation. But do you have to know that to do this problem? No. I mean, it's just a property that kind of speeds things up a little bit. So, something like that. We will talk about those properties on Thursday. All right, let's get an exponential equation. 81 to the x equals 27. Well, I wouldn't do log base 81. I'd try to break those numbers down. 81 could turn into what? 3 to the 4th power. And 27 is 3 to the 3rd. So that's really 3 to the 4x equals 3 to the 3rd. Now, mathematically, there's an operation that happens here that gets rid of the 3's. That operation is you're saying log base 81. That operation for this problem, what's the base on both sides? It's 3. So the operation that actually gets rid of those is log base 3. And that gets us 4x equals 3. So you take the log base that's on each side and go from there. And that gets rid of them, actually, is the math that's happening. And then just solve it. The reason you need to know this part is when that doesn't, it's not a nice number over there, like this next problem. 3 to the 5x equals 24. 24 can't be rewritten as 3 to the power. You could write it as 3 times 8, which 8 is 2 cubed, but that doesn't help you really. So on this case, you don't have a nice cancellation or a nice exponents that should be equal to each other to recognize. So we got to get rid of that base there to get this 5x out of the exponent. To get rid of that, you're going to take the log base 3 of each side. Okay, log base 3, as long as you're doing it to both sides, that makes it legal in an equation sense. And if I do the same thing to the left side as I do the right side, it's fair, it's equal, that's what equations do. You have to do the same thing on both sides. So that makes it legal. On the left side, the log base 3 cancels out this 3. And it leaves us with 5x. On the right side, we're left with log base 3 of 24. That's just a number. It's a decimal number, this long. Okay? It's a big, long decimal number. But that's a number, like 13 or something. Okay? It's just a number. It's weird looking, but it's a number. Can I get x by itself? How? I just divide both sides by 5, right? X is going to be log base 3 of 24, all divided by 5. We're going to get a decimal approximation for that. This is the exact solution. We need to be able to get the exact solution. We also need to be able to get a decimal approximation for that. So that's where we're knowing how to evaluate that log on your calculator is helpful. So we're going to take log base 3, so math, log base 3 of 24. So there's that decimal, log base 3 of 24, 2.892789.261, and then it keeps going and run, it just keeps running on there. We're going to divide that by 5. We're going to round to 4 decimal places. Everything we get an approximation for today, we're going to round to 4 decimal places. So it'd be 0.5786. The 5 makes the 5 go up. 5786. And we get that solution out of that. Okay. So when there's not a nice number over here that gets you the same, you can rewrite as the same base, then you're going to have this log base inside of your answer. Okay. Let's look at one more of those. 2 to the 3x plus 1 equals 15. If that were a 16, we could go, 2 to the 4th power is 16, and I could set 3x plus 1 equal to 4 and solve it. But since it's 15, I can't do that. So what log base gets rid of the 2? A log base 2. So I'm going to do log base 2 of both sides. Right? On the left side, what happens with the log base 2 and this 2? They cancel each other out. Get 3x plus 1. What do we know about the log base 2 of 15? What is it? It's just a number. It's a big, long decimal number. That's all we know about it. So how do we get x by itself now? Minus 1. So it's going to be 3x is equal to log base 2 of 15 minus 1. So maybe it helps to put that in parentheses. That it's log base 2 of 15. That's a number. We're going to subtract 1 from that number. Don't subtract 1 from the 15. That's a very common mistake, is to make that log base 2 of 14, and that doesn't work. And the last step, divide everything by 3. I'm just going to divide that entire side by 3. So x equals log base 2 of 15 minus 1 all divided by 3. That's the exact solution. Let's get a decimal approximation for that. So math, log base 2 of 15. And I'm going to subtract 1 from that answer. 2.906890596 divided by 3. Going 4 decimal places. So this is where you've got to be able to round, guys. So I look at the 6 that's after the 9. So that makes that 9 do what? Go up to 10, which means the 8 has to do what? Go up to a 9. So it's 9690. Okay. 9690. We'll practice rounding in today's, or the rest of this chapter. So you got to be able to round correctly. Okay. Not an overly dramatic topic here. A large set of problems to look at. Again, you don't have to do all of them. Pick some from each set and make sure that you can work some of all of them. A lot of material here in this section. But if you can get it down in this section, it makes the next couple of sections easy because we just got to learn a few properties for the next couple of sections, and it works out great for that. Yes, ma'am.